Hey guys, so this is our thread reflection video for the piano project. So piano project is a signal processing project through and through. It covers us through three different ways. It's a circuits application, a digital signal processing application, along with a programming application, all wrapped into one. So it starts with digital signal processing. We take our wave file inputs for all of the keys and then feed it into the spectrogram function on MATLAB, which allows us to visualize the frequency content over time for different frequencies for the specific key. And you can see all of the fundamental harmonic along with all the other harmonic content for each key press. Then we take all of these max, the peak harmonic content, and we find functions that actually allow us to wrap around it. So we know it's an exponential decay, so we can take it in the log domain and find that it looks like a polynomial, and then use least squares to actually derive all the parameters for it. And then later we use the envelope functions derived on the previous slide to regenerate the signals by putting together an array of cosines multiplied by the envelope functions, which would later be fed into the DAC. These concepts relate heavily to ECE 2026 in signal processing, specifically regarding Fourier transforms and understanding how they relate to frequency derivations, then spectrograms and tracking frequencies over time, along with regeneration through the superposition principle. The use of least squares is also covered directly in linear algebra and later expanded upon in the ECE 4252 class, Fundamentals of Machine Learning, which is also covered in the thread.
Embedded programming is also important for any signal processing application you want to do because it allows you to do DSP not just on your computer but on something that you can take. One important thing that we have is making classes. So we have a class here, a key class, which includes the fundamental and harmonic frequencies as well as those envelope functions that we were talking about earlier. And the key class then has functions, which allows you to get the current value given an input time, which lets us get that curve that we saw earlier, as well as some setters for initializing things. Another class we have is the keyboard class, which gives us the keys that we have available to us, the time that keys were pressed, as well as what keys were pressed themselves. And then the functions here in this class allow us to press, depress, and as well as get sound from the piano. We now have a programming flowchart, which gives a detail of our program. So we have up here initialization, and then looping through all of our keys to see if things are pressed, and then getting the value from the piano and writing that to our DAC, which then goes to our speaker. So a lot of this embedded programming is heavily connected to 2036 as well as 2035. Either of these classes can be used for this project. We more heavily focused on 2036 since we were programming in C++ and have classes, but 2035 can be used instead, where classes can be exchanged for structs. These classes directly relate to 4180, the embedded systems class, which is included in the signal processing thread, where you get to learn more about and build embedded systems yourselves.
And finally, we get to the circuits aspect of this, which relates heavily to the analog signal processing side. So again, as mentioned in the other video, the components are made up of the DAISY microcontroller, the speaker, and then the other aspects which combine into the analog signal processing, so the op-amp and the audio amplifier, along with a bunch of passives to build our project. So the complete audio amplifier is split into two stages. There's the inverted op-amp buffer, along with the audio power amplifier. And specifically, the isolated inverting op-amp allows us to do a lot of reshaping on the signal. Specifically, we take our signal coming in from the DAISY, we isolate it, allowing it to center around 4.5 volts instead. Then we have a gain of 0.2, and then we send it through another isolator to center around 0 volts instead. And this allows it to be shaped exactly into the format that is acceptable for the audio power amplifier. The audio power amplifier, for the application for it, we then look at the datasheet for it. And directly take all the components off of it in order to build our circuit that allows us to build our piano project. And both of these relate heavily to the ECE 2040 and ECE 2031 classes. So 2040, the basics of capacitor functionality allows for the fundamentals of isolation. And then there's fundamentals of DC and AC circuit analysis, including op-amps and inverting op-amp buffers, which relate heavily to 4180 along with analog signal processing applications. And ECE 2031 Digital Design Laboratory allows us to kind of do a lot of breadboarding and put all of this whole project together, in addition to doing datasheet analysis. which is how we found the typical application for our power amplifier.
So what this project means to us, this project allows us to create or combine our passion with ECE in itself. All the members of this project are part of some music ensemble here on Georgia Tech, and we got to use our musical love and create something with the Thread signal processing. And our related applications are, we have just reading in audio, doing signal processing, and then putting audio out, which is exactly what we did through this project with our processing in MATLAB. We also have analog processing here through guitar pedals, as well as more digital processing, so like headphones and noise canceling.